Friction is a force that tries to prevent two surfaces from sliding relative to one another. There are two main types of friction, which are the static friction and kinetic friction. Static means lacking movement, action, or change. Therefore, static friction is when the two surfaces causing the friction are not moving relative to one another. The word kinetic means of relating to or resulting from motion. Hence, kinetic friction is when the two surfaces causing the friction are moving relative to one another. Here we can see the formula for static friction, which is Fs equals to Fn, the normal force, times μs, the coefficient of static friction. And here the formula of kinetic friction, which is Fk equals to Fn, the normal force, times μk, the coefficient of kinetic friction. And here we can see the coefficient of static friction is typically larger than the coefficient of kinetic friction. This plot illustrates the standard model of friction. The two regions that we will be focusing on are the static region and the kinetic region. In the static region, the static friction will increase along with the increase in applied force until it reaches the maximum value of static friction. Once we surpass this point with an increasing value of applied force, the object is said to break free, enabling it to move or slide. This one. To keep the object sliding, we still need to apply force, and this is the kinetic friction. We can see that the value of kinetic friction remains constant as we do not need to apply as much force to keep the object sliding as we needed to originally break free of static friction. Here, we are going to look at simple experiments with a circular object on two different inclined surfaces. For both surfaces, we are going to look at what angle is required in order for the object to slide. So let's look at the smooth surface first, which is a book. As we can see, the circular object starts to slide when the inclined angle equals to 22 degrees. Now let's look at the rough surface, which is the chopping board. As we can see, the circular object starts to slide when the inclined angle equals to 37 degrees. Thus, we can say that rough surface has more friction than smooth surface. Hence, larger inclined angle is needed for the object to slide down. This is a free body diagram of the previous experimental setup. We have normal force acting perpendicular to the surface and the weight mg that acts in a downward direction. The weight will then be resolved into two components, which are mg sin theta parallel to the inclined surface and mg cos theta perpendicular to the inclined surface. There is also frictional force parallel to the surface but opposite in direction of the resolved force mg sin theta. So, an increase in angle causes the value of mg sin theta to increase until it exceeds the value of the opposing static friction, resulting in movement of the object. This movement is now only opposed by the kinetic friction. Before I end this video, let's do another experiment in which this time around I'm going to see whether the coefficient of static friction independent or dependent to the surface area of the object in contact. In this experiment, I placed a box on the same book that I used earlier. I then tilted the book to make an inclined plane and then I recorded the angle at which the box starts to slide. So in the first clip here, the broad side is being down. And in the second clip here, the narrow side is being down. So basically, I took measurements of the inclined angle when the box starts to move for both the broad side being down and the narrow side being down. I repeat this process for 5 times each, and then I took the average of the results, as seen here in the table. So I'm going to refer back to this diagram that I also used earlier. As mentioned, the formula for static friction is normal force times the coefficient of static friction. Rearranging this formula, I get static friction over normal force equals to the coefficient of static friction. In this experiment, I'm taking the minimum angle just before the object moves. So this is the angle, here is the angle at which mg sin theta will cancels out the static friction force. So mg sin theta minus static friction force must equal to 0. Rearranging this, mg sine theta equals to the static friction force. I then divide both sides with the normal force, so the left side will be mg sine theta over normal force equals to coefficient of static friction. As seen in the diagram here, the normal force here is actually the vertical component of the weight, which is mg cos theta. So I'm going to replace the n, the normal force, with mg cos theta. Here, I can also cancel out the mg, and then I'm left with sine theta over cos theta, which is tangent theta, and this equals to the coefficient of static friction. With the previous formula that we obtained, we can solve for the coefficient of static friction, which is completed by taking the tangent of the average experimental angle. So, the average coefficient of static friction between these two materials with the broadside facing down is 0.441, whereas the coefficient of static friction with the narrow side facing down is 0.445. These values are very close, and it illustrates that the surface area doesn't make any difference. As long as the objects that are in contact against each other has similar type and condition of contact surfaces, it will have the same coefficient of static friction. That is all from me. Thank you very much.